Cool. Hope you are enjoying it so far. So what we are doing today, we are going to do today, we're going to show you different applications of Gaussian processes and uncertainty quantification. Essentially, the three first talk are going to work like a block. So what I'm going to do first is I'm going to show you how you can use Gaussian processes to do global optimization. So this is called Bayesian optimization. So we are going to be talking about that during the next 45 minutes. Then Rich is going to be talking about approximate Bayesian computation as a way of doing uncertainty quantification. And in the third talk, Mike Goodman is going to show how you can use Bayesian optimization to speed up and improve approximate Bayesian computation. So you can think about these three first talk about somehow like a big block that connect to each other. So what are we going to do here? So this is the ultimate goal of what we want to do. So I've brought here this sentence of Alfred North Whitehead, which says, civilization advances by extending the number of important operations which we can perform without thinking of them. So what we are talking about here is about automation of processes. In particular, we are automation of processes. In particular, we are going to talk about how we can make machine learning automatic, how we can select the best algorithms and the best models for a problem that is given to us, and how to do model configuration with that. And the second point is how can we optimize processes? How can we optimize physical processes or sequences of experiments to achieve some particular goal? So that's the idea of the talk. So a bit more formally speaking, we are going to be talking about global optimization problems, in which we're going to have some function f that I've written that is well-behaved. In particular, well, you can think about well-behaved function like something that is continuous, differentiable, but more specific definitions can apply in different contexts. And in principle, we are going to consider the problem of minimizing this function in a bounded domain. Also, in terms of the domain in which the function is defined, you can have more general definitions, but this is the standard case we are going to consider here. So the problem is very easy to state, but very hard to solve. It's finding the global minimum of this function in the domain that we have, right? So these are just an example, just some examples of some functions from optimization benchmarks that you can find easily on the web, in the literature. What is interesting about this problem, and what we are going to talk about today, is that the function that we want to optimize, we are going to assume that this is explicitly unknown, and this can be because of different reasons. It may be because simply the function that we have corresponds maybe to some likelihood that is written in a very long piece of code. So we don't have an explicit form of f, but what we can do is to evaluate it in some particular points of the domain in which we want to optimize it. It can also be because simply the f is embodied in some physical process that we want to optimize, and we don't have access to it. And every time we want to evaluate our function, we have to run a wet lab experiment. The function is going to be multimodal. The evaluations that we perform when we try a particular value of the parameter set may be also perturbed by those. And this is probably the most important of all of them. Well, all of unimportant, but this is quite characteristic. So what we're going to do here is that evaluate f is very expensive. Is very expensive. And I've just brought some examples that I'm probably you identify yourself with some of these. So imagine that you want to do model configurations. You have support vector machine, or you have a deep neural network. There are many things you can do with this type of models and algorithms, but it's crucial to find the parameters well, right? To make the work in a practical case. So you can think about, so you have a deep neural network, you need to select the number of layers that you have, the units per layer, the weights, learning rates, etc. If you are training a neural network in a very large data set, this can be very expensive, so you have to be very smart and the way you allocate your budget to the different parameter sets that you try. Just another example is how you optimize web pages. This is called A/B testing. So imagine that you are designing a web, and what you want to do is to maximize the number of clicks that you have, downloads, purchases, whatever. So you can think about some parameterization of your web in terms of, well, where do I allocate the pictures, where do I put the buttons, etc. And you can run an experiment in which you run the web for a few days and you evaluate these different objective functions that you may have. Another example, and we have been working here in Sheffield, is how you can optimize a physical process. So in this project, what we were doing, we were taking cells, and we wanted to use the cells as mini factories to overproduce certain protein of pharmaceutical interest. So what we were doing there was basically rewrite the genetic code of the cell, design synthetic genes to speed this process up, to produce more protein with the cells that we have. So the problem is that, as you can imagine, to run these lab experiments is very expensive. So we had to be very careful about what genes we were designing. So that's some examples. So the first thing you can think, well, if I want to optimize this function and I don't have direct access to it, well, I can simply do grid search, right? If I really want to be sure that I'm hitting a point in the domain that is close to the minimum, I can do grid search. So imagine that your function is Lipschitz continuous. So basically, the distance between the output is bounded by the distance between the input plus times a positive constant. You can say, okay, if I do grid search, I have a function in which I want to hit a point in which the distance in the output between the optimum that I get and what I'm proposing is smaller than some tolerance epsilon. This is the error I'm willing to assume. Then imagine if your function is defined in a d-dimensional hypercube, basically to guarantee that you hit a point with this distance to the optimum is this quantity here. So if you think on an example in which the constant, Lipschitz constant is 10, in which the tolerance is 0.01, and it's an example in 5 dimensions, you have this number of evaluations you're doing. So, and one of the hypotheses that we were making at the beginning is actually that the function is very expensive to evaluate. So this is something that clearly we cannot do. So all we are going to discuss about here is how can we be smarter about different strategies to find something optimal or close to the optimal of the function. So, so you can think about, okay, well, I know I don't know my f, but I can define a quantity like this. That is kind of the standard quantity that is used to evaluate how good a Bayesian optimization algorithm is in theory. This is the regret. So I say, okay, I'm going to change my problem of finding the optimum of my function that we had at the beginning by a problem that is to make a series of evaluation of a function that minimizes this cumulative regret. So basically what I'm computing here is the distance between, well, where the value of the function at the optimum, that I know that I don't know that, but if I knew it, I could compute this quantity here in a way that, well, if I propose an algorithm that is minimizing this regret, I'm proposing an algorithm that is good, right? Because in the ideal case, if I were hitting the minimum from the very beginning of the sequence till the end in the optimum of the function, this regret will be 0. We are not going to use this a lot, but if you read Bayesian optimization papers, you will see that that's the goal. So when you study the theoretical guarantees of the different algorithms, you study them in terms of how they minimize their regret. In general, there are other measures for different objectives that you may have with your optimization, but this is a standard quantity. So if you see what we are doing here, basically we had an optimization problem at the beginning, and we have replaced that optimization problem by a decision problem, that consists on defining a sequence of evaluations of the function. And as I said before, you can think about this like, well, I'm tuning my machine learning algorithm, I'm optimizing my physical process, I'm designing a sequence of experiments. And as we have been seeing these days already, so this is all a problem of inference, this is a problem of uncertainty quantification, because now we have a system, we have some epistemic uncertainty about the system that we are analyzing, and what we are going to do is to use probability theory and Gaussian processes to deal with this problem. So just wrapping up until here, so we have this optimization problem that we want to solve, this function. We don't have gradients, we don't have even an explicit form of it, we just have finite number of evaluations that we can do. What we are going to do is to solve the optimization problem through a decision problem of defining a sequence of evaluations of this function that will ideally minimize the regret that we were mentioning before. And we are going to treat those decision problems as inference, as we are going to use inference to address that. So this is the idea. So, and this is probably the most important slide of the presentation, right? So this is trying to summarize everything that we have said so far. So what I'm going to tell you is, okay, there is a function that is a continuous function. It's a differential. Is differentiable. Is defining the interval 0, 1. I know what function is, but you don't. But what I'm telling you is that under those assumptions that the function satisfy, I've made 4 evaluations that are exact evaluations of the function, so there is no evaluation noise here. And I got these 4 points over here. So you can think about having a more complex design space, multidimensional object that you are optimizing, but let's keep it simple. So this is essentially the situation. We don't know the function, we just have 4 evaluations of it. And now what we want to do is, well, we want to know 2 things. First, ideally, because that's the problem that we want to solve, we want to know where the minimum of the function is. But that's probably hard now, just with 4 evaluations. So if I'm telling you, okay, I'm giving you another potential evaluation, another evaluation of the function that you can do, where would you take that evaluation? So remember, this is a continuous differentiable function. I've made 4 evaluations. This is the result that we have. So if you have to make the decision of where to locate another evaluation of a function, where would you do it? Okay, so first question, how many of you would make an evaluation right in this point? No one, right? Because we have something that is already better, right? So how many of you would make an evaluation of a function in this interval over here? Yeah, many? Why would you do that? What's the intuition about making an evaluation of a function here? Say again? Because it's close to the current minimum that we have. Something else?
Gradient between the right 2 points.
The gradient. So okay. So if I assume that my function is elliptic continuous, so basically I know what's the distance between these 2 points. So I can assume that the distance. This is the level of change that I can assume that my function has. So maybe this is something like this, or maybe the function, the idealized function that some of you may be thinking about could be something like this, right? So it's a continuous function. It goes through the points. What I'm representing here is simply the location where the minimum of the function is, which is here, right? But many of you say that, okay, I think the function, I should evaluate the function in this interval. So probably every one of you have a different conceptualized version of the function that we are optimizing, and you have something like this, right? Okay, so we can play this game a bit more, and we can print other function that you may have in mind. And maybe some people, not everyone, was agreeing that we should evaluate the function here. Some of you will say, okay, probably the minimum is over here, so maybe you were thinking that the function was like this, right? So we can keep playing this game and generating more and more samples of this function that we want to optimize. What we are doing here, as I said before, is simply counting where the location of the minimum of those functions are, right? And we are just computing the histogram. So imagine that we generate many more, and we take this to the limit, and we generate infinitely many samples of this function that we want to optimize, and we basically compute a smooth version of the histogram, which is a probability distribution. So basically, okay, so what happened here? So what just happened, and probably you already know where I'm going with this, is that, okay, so I gave you some information about how the function looked like. So you idealize the shape and the form of the function, and but we are not interested in the function. We are interested on a particular feature that the function has, in this case, the minimum, right? So what we have done is by making some assumptions on the function that we have in mind, we have generated a probability measure about the function that we have combined with the information that I was giving you about the 4 points that in which we had evaluated the function, and we have derived the probability distribution of the minimum of the function, right? So, and now if we come back to the previous slide, now what we can do is to say, well, I have this probability distribution that is representing now my beliefs about where the minimum of the function is. So what I can do is I can do this probability distribution or a functionalities of it, like it's done in entropy search, but I will mention this later, to make the decision of where to make the next evaluation of the function. So I'm using here the distribution over the minimum, but you can think about, okay, when I generate these functions, when I simulate these functions, I can basically compute, okay, which is the relative gain that I expect to have with respect to the current minimum, and you will be deriving something like the expected improvement that David was mentioning yesterday. So I'm using here the distribution over the minimum because I think it's very natural to understand the intuition about Bayesian optimization, but essentially you can use other forms and other features of these samples that you have. So basically now there is a direct map between direct mapping between this reasoning that we have done and what actually Bayesian optimization is doing, right? So in Bayesian optimization, that was first proposed by Mokus a few years ago already, 1978. So what you do is you choose some probability measure over the function that you want to optimize. You combine that with the likelihood, and then you use the posterior distribution to decide where to evaluate the function next, right? And the way you decide where to evaluate the function next is through something that is called acquisition function. In the literature, some people call it as well like loss function, utility function. There are many names for that. But in this presentation, I will use simply acquisition function to decide where I'm going to take my next evaluation. So you see there are two key elements in this process. The first key element is a model that we are going to feed to the available evaluations that we have about the function that we want to optimize. And the second element is the acquisition function, which is going to be built on top of the model that we have built that is a surrogate of the function that we want to optimize, and that is going to help us to make the decision of where to evaluate the function next. So basically, what I'm going to do now is I'm going to visit these two elements. I'm going to talk a bit about the prior measure that we will be using for the function that I guess you all assume you all know already what it's going to be. And I will be discussing a bit what possible acquisition functions are to solve this problem. So, probability measure over function, Gaussian process. I don't have to say a lot about this. So you had already several talks discussing what Gaussian processes are. So this is what we're going to do. So we take some evaluations. We are going to fit a Gaussian process, and then we will use the Gaussian process to define this acquisition function. Some people like using other type of models. So some people use random forest or other model for solving this problem. But up to all the experiments that we have done, Gaussian process is the best that you can use in this case, especially in regimes in which you don't have a lot of data, right? Which is typically the case when you do Bayesian optimization, especially during the first iterations of the process. So this is a probability measure. Acquisition function. Okay, so you remember before we were deriving this probability function, this probability distribution over the minimum of the function, and we were saying, okay, we can use this to make the decisions of where to evaluate the function next, right? You can use that probability distribution to define an acquisition function, but you need to keep in mind that pretty much any acquisition function that you define is going to be a balance between two different things that you can make that you can use to make the decision. So you remember when I was saying, okay, what do you think that why do you think that the minimum of the function was in this interval over here? Someone was saying, oh, because that's close to the minimum, right? So what are you doing there? So what you are doing is basically exploit what you know about the function, which is that there is a value that is very low. And well, it makes sense to exploit that information. And if that value is very low, probably the minimum is very close to it, right? So that's called in the Bayesian optimization literature to do some exploitation of what you know, right? It's basically you are using values, not of the points, but you tend to select values where the mean of the mean of the Gaussian process is already low. Or you can do exploration. Okay, we also have some large intervals here where we probably don't know what's going on. We have very large error bars in the Gaussian process. So it may be worth but just spending some evaluations on the function in regions in the domain where we don't know what is really happening, right? Because it may be that something good is found there. So just to illustrate this, I like using this picture. So you can think about this like going to a restaurant, right? So when you go to a restaurant for having dinner, or you go to a brewery and you want to select your favorite beer, you want to optimize some sort of satisfaction that you get with the food that you are having, right? So if you have been in the restaurant before, you can say, okay, if I really like how the tacos are in this restaurant, I really like them and how they prepare, I'm going to exploit this, I'm going to order tacos, right? Or you can just say, okay, I'm going to explore, I'm going to get something of the house specials that I have never tried before, but it may be that I don't really like it, or it may be that I like it a lot. So it may be that I'm finding something that is interesting for me. So this is just a way of illustrating how Bayesian optimization, I think this is one of the most interesting things of Bayesian optimization, how it's really emulating the human decision process. So we have some priors about some decisions that we have to make. We have some updates when we collect evaluations. And then we change those beliefs and we change the way we optimize our own utility functions. So I recommend you to read this paper. That's very interesting. So what they do is basically they compare optimization problems in dimension 1 with the way people, just by clicking on a screen, are trying to minimize the different benchmark of objective functions that they provide. What they saw is that actually, at least in those experiments in dimension 1, humans are better than any optimization method doing that. And if there is a method that is close to what the human is doing, is Bayesian optimization, which makes sense because it's what is emulating this decision process. So just a few examples of different acquisition functions that we can use. So this is the GP upper confidence bound that was proposed in this paper over there. I'm calling it lower confidence bound because we are minimizing and not maximizing. I like this acquisition function because you see very explicitly the 2 bits that any acquisition function balances, right? Which is the exploration exploitation. So if you see, when you define the upper confidence bound, a point in the domain, given some parameters of the GP and some data set, this is basically the mean plus a positive constant times the standard deviation of the Gaussian process. So you see that by selecting this parameter, what you're doing is you're giving more weight to the variance or to the standard deviation of the GP, or you are giving more weight to the mean. By selecting this parameter, you are exploring or exploiting more in the search that you are doing in the space. So this is just a GP fitted to the 4 data points in the example that we had before. These are 95% confidence interval. This is the mean. This is how this utility function, this acquisition function, looks in this particular case. So now what we have to do is we want to use this acquisition function to select another point. We will maximize this, and we say, okay, we maximize this, we get the point that is over here. We will collect another evaluation there, and we will proceed if we have more budget for that. This is That's a very interesting paper. This is an interesting acquisition function because it's one of the few acquisition functions for which you can actually prove things about how you are converging to the optimum, right? With other acquisition functions, you can do that, but this is one of the few for which it's possible to do that. Another example, David was mentioning that yesterday already, is the expected improvement. So, well, remember those sample parts that we had before. So now, in each point in the domain, what you are basically computing is, okay, which is the expected gain that I have if I were sampling in one of those points. So this is my current best. So I don't expect to gain anything given my current GP if I sample here. So expected improvement drops to 0. I say there is nothing, you have nothing to do there. But if you evaluate somewhere over here, well, I have a level of uncertainty that allows me to tell you that there may be something interesting going on there. So you probably should evaluate the function there. Expected improvement. Information theoretic approaches. This is linked to the probability distribution that we were deriving at the beginning. So you can think, okay, I'm going to use that probability distribution and the mode of that probability distribution to select the new point in which I want to evaluate my function. That's true, you can do that, but you can even use that probability distribution in a smarter way, which is using it, doing entropy search, in which what you're basically doing is this is one of the few non-local acquisition functions that you can use, because what you do is to say, okay, I can compute the entropy of my probability distribution, and what I can do is I can compute the point in the domain that reduces this entropy a lot. So this is the entropy of my probability distribution. Okay, what's the entropy? That's the reduction in entropy that I have when I sample the acquisition function, the objective function in here. So I fantasize what is going to happen if I take a point here, so I can calculate which is the reduction in entropy that I would have. So that's a acquisition function that was proposed by Philip Henning, and then José Miguel Hernández Lobato proposed a different approximation of acquisition, but essentially the two papers are proposing the same acquisition function, but different approximations to it, because it doesn't have closed form, and you have to do some work to get it done. So that's the idea. So these are 3 acquisition functions. There are others, like you can use Thomson sampling or other acquisitions. The literature is full of acquisition functions for different problems. You can have a look to them, but because it's very interesting. So so far, we have visited the model that you're going to use a Gaussian process. What the acquisition function represents, the 2 main bits, exploration, exploitation, and this is just a small illustration of how the entire process would work if we want to optimize this function. So this is the true function that I was sampling from, the dotted line. What I've done is to start with an evaluation of the function in the center of the domain. You need to give something to the GP to start. So either you start with one observation, or you have a problem that is more complex, and you have a problem in which you can allow yourself to have certain number of evaluations at the beginning of the process. You can do things like use high discrepancy sequences like Sobol sequences, Latin hypercubes, or even if in a very simple case, you can simply sample randomly the domain in which you want to optimize your function and then proceed on a Gaussian process fitted on that. But in this case, we are just going to fit we just have one evaluation in the center. This is expected improvement. So what expected improvement is telling us is, well, in this region and in this region here, you can collect a point. Doesn't have any preference whether we do it here or we do it there. So just, I think I didn't mention this. So the yellow line is representing my current best. This is the mean of the GP. These are the confidence interval. So I have many choices here. I'm just going to the extreme of the interval over there. So I collect my new point here. I have the reduction in the variance of my GP. I know that I'm doing exact evaluation, so I have certain certainty around the point. the acquisition function updates accordingly. So we have done something. We haven't done much. We still have a lot of points to choose. We don't have any preference, so we go to the extreme on the interval. And now interesting things happen, right? Because if you see, well, here we were evaluating the function, and the outcome that we were getting was actually worse than this one. So the region that we are discarding, in which we are not going to evaluate the function anymore, is of this size. Now we have evaluated the function, and we have done in a point that is much higher than our current best. So that means that we can be sure that given what our GP is telling us, that we have a larger set of points in which we don't need to evaluate the acquisition function, because we are already very far from something that we have found is good, right? Again, so we repeat the process, we evaluate there, we go have do another point. And now if you see, we are already focusing on the region when we know the optimum of the function is. And now look what happened. When we collect an evaluation there, look, basically now, because this is our current best, we are discarding all this piece of the space, and we are not going to make any evaluation there. Now we have the acquisition function and the GP, they have found something interesting in this region, and this is telling us that, okay, whether you evaluate here, you either evaluate here or there, because I think that's where the minimum of your function is. So you take a few more evaluations, and after some of them, well, you see that you have converged to the minimum of the function. Look how look at the distance between the evaluations at the first phase in the optimization, in which we were basically exploring the space. We collect 3 points over there, nothing interesting happened. As soon as something interesting happened here, we focus here and we convert. So this is showing you how smart the system is, right? So you can think about solving this problem by initial grid, in which we are not doing anything smart, because we are giving the same importance to a sample that we collect here to a sample that we collect here. But actually, now that we know things, because we are doing all this process, we know that something interesting is going on here. Right? Any question? Yep. Yeah. That could happen, but you have some smoothness assumption in the GP when you do the fitting. So if you know you have information that can happen to your function, you may need to encode that in the covariance of the GP, and that will result in a different calibration of the uncertainty, and that will allow you to consider those cases. Yeah.
You're doing that point by point, aren't you?
Yeah.
How hard would it be to generalize that so you consider several points? Yeah.
Next slide.
Following on from the first question, so in terms of your hyperparameters of your covariance function, I'm assuming you need enough points at the start just so that you can estimate them reliably.
Yeah.
Do you actually then go on to refine those hyperparameters and go back in time and say,
Yeah.
was my decision correct?
You are going to see that this afternoon. You are going to work with GPyOpt, that is a library that we have developed here in the group. There are different things you can do about that. Actually, the funny thing is that you need to, if you're using a GP, if you're doing MLE on the hyperparameters, you need to optimize the hyperparameters, right? That's probably not the best thing to do, especially in the first steps of the optimization. It's better to do MCMC, so everything becomes more robust, and you don't have to replace an optimization problem with another optimization problem in your model. But you will see that this afternoon.
The p-min function you showed at the beginning, like probability distribution.
Uh-huh.
Is that in some sense the optimal but intractable acquisition function? Or
That's one of the, so that's not the acquisition itself, so you can use that via entropy search by finding the point that
not actually accessible, right?
it doesn't have closed form, so you have to approximate it. There are different approximations. One you can do is you can do it with Thompson sampling, so you can sample, you can approximate. If you have a stationary kernel, you can approximate continuous samples of the GP. You basically have the histogram and some smooth version of that, and you have a pack that is probability distribution. Is not necessarily the optimal choice. Is an acquisition function that works very well in many problems. It's an acquisition function that is not very greedy. So if you compare that acquisition function with what the expected improvement do, if the problem is relatively simple, the expected improvement may do better because it can converge very fast to the optimum while entropy search still explore a bit more. But if your problem is complex, you probably want to entropy search. The price that you have to pay to compute the acquisition function in case of the entropy search is much more expensive than computing the expected improvement, which has a closed form, and you have gradients and everything, so then to optimize the acquisition function is easy. You don't have that in entropy search, so you need to optimize in a set of landmark points, and things can be a bit more expensive in that sense, but an acquisition is much more fundamental. Well, not much, it's a different thing. You're searching for it's a different criteria. So the way you're balancing exploration and exploitation is different. Yeah.
Another follow-up question on the smoothness assumption. Is
Yeah.
there a way to detect failure modes if our smoothness assumptions are wrong, or do I just get an answer and it tells me I'm really sure it's this and might completely wrong?
There are all sort of tricks that you can do. So to detect failures, you mean when you fall to some local minimum, for instance?
Because you assume it's not in the left region, but it might be in the left region if it's wiggling fast enough.
Yeah, so you can have a non-heteroscedastic model to capture that. You may want to do optimization in some sort of hierarchical optimization. So maybe you first want to start with some global search, identify regions, and then to focus on those regions and do the optimization. So there, it depends on your problem. There are some papers in the literature dealing with that, but this is still some kind of an open question where how should I escape from local minimum. Something you can do, and we will mention that in a minute, is when you do batch selection. When you do batch selection, you have different evaluations. You can perform different evaluations of the function at the same time. So if one of them is focused on the region, then you can spend the others evaluating what is happening in different regions. So you can explore different regimes, blah, 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 and solve the problem that way.
When you evaluate the function at the second point,
Mm-hmm.
I'm assuming that the function lives within a certain interval of interest.
Yeah, so in principle, we are optimizing the function in the interval 0, 1. There are some words that consider the same problem when you don't have a bounded domain. What they basically do is they kind of learn on the way where the interesting things are happening. What they do is they don't have an interval, but they use a trick that is basically a penalization of the acquisition with some indicator function that say, okay, yeah, I start in a very large domain, I start evaluating, and then I reduce the domain by penalizing, by basically multiplying my acquisition by some indicator function that drops it to 0 out of regions of interest, and you start focusing on finding the optimum.
Does the acquisition function have to be continuous, differentiable? Or can you have sort of irregular?
It doesn't have to,
Yeah.
but it's a good property if it is. And the reason is because, and this is actually the next slide. All we are doing here is to replace this optimization problem that was unsolvable for us because we didn't even know what this guy is. You don't have explicit form of it. By a problem in which this guy, which is the acquisition function, in the case of the expected improvement, for instance, we have gradients, we have an explicit form of it, we can use conjugate gradient or BFGS to optimize this. So the simpler this optimization problem is, the better for us. Because if we are replacing this optimization problem by an optimization problem in which the acquisition function is very hard, is very expensive, and very hard to optimize, we are not solving anything. The trick here is that we are replacing something that is complicated by a sequence of optimization problems that are simpler than the original one. Yep. Yep.
So this could presumably be used for noisy function.
You can use it for noisy function. You just need to adjust then the noise in the Gaussian process. Yeah, but it holds, everything holds the same.
And is this a different problem to if you know your number of evaluations in advance?
You know the number. This is next slide is parallelization, and I will mention that briefly. I think I have 4 minutes or something like that. So very briefly, these are the 2 points. One, parallelization, and the other one, non-myopic method. So if I know beforehand how many evaluations do I have, how is that going to affect my policy when I select the points? So imagine you were saying before, instead of one evaluation, I can do multiple in parallel, right? For the same cost. If they cost differently, or if take different amount of time, the story is still parallel, but slightly different. So this is something that we have on here. Very briefly, what we are doing in this work is, so imagine that you have this acquisition function. It's multimodal, so if I have 3 evaluations, I want to explore the 3 modes. Right? So what we do is a heuristic that is very cheap and work very fast. Basically, what we do is, well, we define in some sort of way some penalizers that drop the value of the acquisition function in the points that we have already collected, so we can explore the different modes of the acquisition. This is a way of doing it. This is something that we have done here. We have compared this with some results in the literature. These are all batch Bayesian optimization methods. And this is just one of the experiments that we ran, but we observed that these are for this criteria working with 2 different acquisition functions, and we have observed that that works very well. So there are a big chunk of the Bayesian optimization literature is actually about how to parallelize this, because it's a very natural idea. So there are many papers. If you want more references, I can give them to you. I don't have time to speak much more about this, but it's a very interesting problem because you need to be very smart in the way. Yeah, very practical problem. So yeah, because you can think you have multi-core problem, or you can run wet lab experiments in parallel. You can do all these type of things. The second question is, well, what happens if I know in advance the number of evaluations that I have, which is basically saying, well, I have 10 remaining. I have budget for 10 remaining experiments. This is a very interesting question because all these acquisition functions that we have been discussing, they are called what is called myopic, is that they are selecting the next evaluation as if that evaluation was the last one. But we may know in advance the budget that we have for that, right? So imagine that this very simple problem in which there is some function that you are minimizing in this interval here. But if you don't have any information, you may want to select the center of the interval, right? So I select this one, right? But if before knowing anything else, I tell you that you have another evaluation, and you already have fixed this one, you may want to go from subdividing the remaining rectangles. And there are optimization methods that are actually doing that. So this is happening because I told you that you have one evaluation, and then once you made the evaluation, you made the second one. If you knew from the very beginning that you have 2 evaluations, you will never do this. You will select the 2 evaluations equally spaced, covering the domain. So this is just a way of illustrating that knowing the budget that you have for doing the optimization affect the policy, affect the way you may want to select the evaluations of your function, right? So we have been working on this problem. There is a lot of things to explain about it. Basically, the main complication is that you have to integrate out all the future steps that your acquisition is going to make before when you make the next evaluation. You need to integrate that out. That's very complicated because that is a nested optimization, marginalization problem. It's full of complications. So basically what we did in this problem was to propose an acquisition function that was an approximate version of that. And we call it GLASSES. That then stands for global optimization. We look ahead through a stochastic simulation and expected loss search. So there's a good acronym to say that we are relieving the myopia of the Bayesian optimization, right? The most interesting thing, I think, about this algorithm is that when you make a decision, it depends on how many remaining evaluations you have it automatically select the balance between exploration and exploitation. So if you have many evaluations to do, you are going to have something like this that is going to be very explorative, right? So if you can go many times to the restaurant that you like, you can try different things, right? You can be more explorative. But if it's the last time you are having dinner in that restaurant, you are going to be more greedy. You are going to get something that you like. So by considering this feature of the optimization, by considering that you have a limited budget of evaluation, you can automatically find the optimal balance between these things. So I think, well, we run this, we compare with other acquisition functions. This is Glasses. This is a benchmark optimization function. We're comparing, and we saw that we're actually getting good results. So that's basically all I have to say. Now Rich will give a talk about approximate Bayesian computation, and then Michael Goodman will talk about how to use Bayesian optimization to improve approximate Bayesian computation. So just to wrap up, so Bayesian optimization, I think is a great tool to automate processes, to do experimental design, to configure parameters of machine learning algorithms. You are going to be working this afternoon with GPyOps, so you are going to do all this by yourself this afternoon. The model and the acquisition function are the two most important bits that you need to consider. We have been discussing those. And there are many open questions like, well, when you want to use this in high dimensions, when you have a multi-output, you have a multitask optimization problem. There are many things that you can do, but I've just mentioned a couple of them in which we have been working. So I think that's it. I think we can move to Rich. Yeah. Any question? While yeah.
Just a quick one. What size of dimension have you tested this up to?
Yeah, that's a good question. So these typically work well. So if you have up to dimension 10, that's fine. If you have more than that, you need to start thinking carefully what type of covariance function you select. So something you can do, you can go for additive models. You can go. There is a paper they propose. It's called Rainbow. They do random projections. You need to start doing some smart selections if you want to use it, because yeah, with higher dimensions, the model is going to collapse. Yeah, you have those problems also when you do the optimization.
Just a quick question. What about constraints when you optimization under quite a series of constraints?
Yeah. So this afternoon, I'll show you a notebook in which you can do Bayesian optimization with constraints. There are two different cases. One is when you know the constraints and when you don't know the constraints. When you know the constraint, you can simply penalize the acquisition function, drop to 0 values you are not interested, and then you select there. If you don't know the constraint, you can learn the constraints with another GP. So whenever you try to evaluate the function, you get back if that's a feasible point or not, and you learn the constraints on the way as well. Yeah. How's it going?
Yeah, sorry.